Hi, everyone. Welcome to the second part of Lecture 21. In this lecture, we're talking again about icy moons in the outer solar system and the prospects for life existing on these moons. In this segment, I'm going to zoom in on three moons in particular, which may be some of the best places where we might find life in our solar system. So the three moons that I want to focus on today are Europa, Enceladus, and Titan. And throughout this lecture, I'm going to give you a little bit of explanation as to why these moons are special and what makes us think that these might be good places to look for life. So, as a reminder, we have talked about this before. Most of the solar system's water is found in objects far from the sun. And that's just because out there, the water was in ice form when these planets and these objects and these moons were created. And ice is easier to stick together than water vapor. So, a lot of ice was able to be accumulated in these relatively small objects. So if you look at the objects with the most water in our solar system, even though Earth is by far the largest of these objects on this list, it doesn't have as much water as many smaller objects, such as moons like Ganymede, Titan, Callisto, Triton, Europa, Dione, and Enceladus, and also the dwarf planet Pluto, far out in the solar system. And that's just because Earth formed close into the solar system where water was in gas form, and therefore it's not able to accumulate as much as these objects farther out. And you'll also notice that all three of these moons that I just mentioned to you are on this list of the objects with the largest oceans in the solar system. Enceladus is a relatively small moon compared to these others, but a large fraction of it is made of water. And Europa and Titan are some of the largest moons in the solar system. So, as a reminder, even though these moons are far away from the sun, so far away that all of the ice should be frozen if there was no other heat that they were getting, they're being stretched constantly by their host planet. And this stretching, this heating, is causing them to warm up. And in this video, we're showing an analogy to that, where this woman has this piece of metal, which she is bending and deforming back and forth. And you can watch in the infrared camera, which is going to show up in just a second, that this piece of metal becomes brighter because it's getting warmer as a result of her deforming it and making it stretch back and forth. This exact same process happens when objects orbit other objects close by with gravity. So in this case, we're watching the moon orbit around the Earth and causing the Earth to bulge a little bit. This is even more extreme in cases such as moons around Jupiter, because Jupiter has a much stronger gravitational field than either the Earth or our moon. And it can greatly increase the strain on the moons that orbit close to it. So for example, in this case, we're showing the moon Europa, which is getting stretched back and forth as it comes very slightly closer and leaves a little bit further away from Jupiter during its orbit. This stretching helps keep the water inside of it warm enough to be in liquid form. So as I mentioned, one of these moons that we've identified as a potential habitat for life in our solar system is Europa. Europa orbits Jupiter. It's one of the four major moons of Jupiter, which we call the Galilean moons because they were discovered by Galileo back in the 1600s. And it happens to be the Galilean moon that has just the right amount of heating from the stretching due to tides to make it potentially a good place to live. So here's a diagram of the inner moon system of Jupiter, the major moons, the Galilean moons. The moons are in order of closest to Jupiter to farthest from Jupiter: Io, Europa, Ganymede, and Callisto. Io is very close to Jupiter, and it experiences the strongest tidal stretching of all of them. And in fact, it's so tidally stretched that it's just constantly under volcanic activity because its interior is molten. Io has the most volcanic activity of any object in our solar system. That's probably too much heating. It makes it counterproductive for it to be a good place for life to exist. The more distant Galilean moons, Callisto and Ganymede, have the opposite problem. They don't come quite close enough to Jupiter, and therefore they may not have much liquid water because they're just not getting heated that much by the tides. But Europa is kind of in this sweet spot where it gets stretched just enough to keep it molten, but not so much that it's constantly spewing out volcanic material and making it an inhospitable place to live. So here are some images of the surface of Europa. There's a couple things to note here. One of them is that there aren't that many craters on Europa. That's a sign that Europa's crust is relatively young. It's made of ice, and it essentially gets replenished. So every time a object crashes into Europa and would create a crater, eventually more ice forms on top of it. That means that this object is geologically active, sort of in the same way that magma flows over impact craters on Earth and essentially covers them over, or they get weathered down in other ways. So in the case of these icy moons, it turns out that water will play a similar role to magma on Earth. So liquid water under the surface is similar to magma, and ice on the surface is similar to the rocky crust that we walk around on. The other thing to note are these big cracks in Europa's surface. These cracks are indications that everything underneath may occasionally spill out, and we've in fact seen some evidence of that. Magnetic measurements of Europa from the Galileo spacecraft, which is a spacecraft sent by NASA in the 1990s to the Jupiter system, have suggested that there is a liquid water ocean underneath the surface of the planet. And this is a particularly exciting thing because, as we know in our studies so far in this course, liquid water is very important to life here on Earth. And the fact that this may have a similar geology to what we see on Earth makes it possible that there may be similar life as well. So for example, we think that there's a rocky crust underneath the water layer in Europa. So perhaps the interface between the rocky crust and the water ocean could be an interface similar to hydrothermal vents like we see on Earth, where life may exist, or where life does exist. Also, the fact that we have a icy layer on top of this liquid water ocean doesn't necessarily preclude life, because we've seen in cases deep in Antarctica underneath ice shelves that life can exist down there. Here are some images from the British Antarctic Survey looking at water pockets very, very deep buried underneath the ice shelves in Antarctica. So it's possible that there's something living underneath in these oceans that's in some sort of analogy to what we can see on our own Earth. The next moon that's a particularly exciting target for searches for life is Enceladus. Enceladus is a moon of Saturn, and it's relatively small. You can see that Enceladus has some similar features to Europa, though. You can see these cracks in these ice channels on its surface. As I said, Enceladus is not a particularly large moon. You can see here that it's only about the size of Great Britain in terms of its extent, so much smaller than the Earth itself and much smaller than the other moons that we're talking about here. But what's really exciting about Enceladus is it has these plumes. So the Cassini mission, which is another spacecraft sent by NASA to explore the Saturn system, has gone and flown around, and it's seen water vapor and other materials escaping from underneath Enceladus into space. And because we can see these plumes, we know that something underneath there is liquid. We can take these beautiful images with Cassini, and occasionally Cassini also flew through these plumes and was able to study what the materials are in those plumes and see what, in fact, that material is made of. And what they found was very exciting, because they found not only water vapor, which is what we kind of expected, but they also found organic molecules, and not just simple organic molecules. They found relatively complex ones, rings of hydrocarbons and such. So this means that all of the building blocks for life as we know it are there in these plumes of Enceladus. So perhaps there's something going on underneath the surface that might resemble or might even be life, kind of like we know it. The final moon that I'm going to talk about in this segment is Titan. Titan is another moon of Saturn. It's the biggest moon around Saturn. And Titan is a really unusual object. You can't see its surface from space. It's covered in this thick atmosphere and this thick layer of haze. And underneath this layer of haze, as this work I'm going to quote from says, Titan is in many ways the most Earth like body in the solar system. And there's a couple of reasons for that. Mostly it's because of its atmosphere. So it's a large moon, it's larger than the planet Mercury. And unlike most of the other moons in the solar system, it has a thick atmosphere that's mostly made of nitrogen. The other constituents in this atmosphere are methane, so another organic molecule, another hydrocarbon, and then trace amounts of other organic molecules. The atmospheric pressure on Titan is very similar to that of Earth. It's only about 50% greater. Now, the temperature, of course, is much colder because Saturn orbits very far away from the sun. But the similarity of the atmosphere makes it a potentially exciting target. The other interesting thing about Saturn is that methane is very similar to how water works on Earth. So instead of raining water as it does on Earth, on methane on Titan, it might rain methane, and methane might essentially produce lakes and rivers and erode the surface in a similar way to water doing this on Earth. We have flown by Titan with the Cassini mission again and measured its gravitational field. This is a difficult measurement to make, but it suggests that there's some deformation of Titan by Saturn due to the tidal forces, and that deformation is consistent with the interior of Titan having a subsurface ocean. It's hard to explain the exact way that Titan deforms otherwise, as we can measure by essentially measuring how strong Titan's gravity is in different locations. So again, this is another case of a world where there seems to be many analogies to Earth. There's this sub-layer ocean. There's a thick atmosphere. There's this active geological cycle, this active meteorological cycle where we have methane filling in for water as it is in our solar system. And finally, there's these possible eruptions of liquid water, which would be cryovolcanism. So essentially the same process as happening on Europa. We're a little bit less confident about that on Titan because we haven't seen it flying through space because it's harder to look at the surface of Titan, but that may be happening as well. And I wanted to finish with these beautiful images from Titan. Back in 2005, one of the components of the Cassini mission was a probe called Huygens, which was built by the European Space Agency and which flew on the belly of Cassini all the way to Saturn. And when it got there, it dropped off and it parachuted down onto the surface of Titan. And it took these images. So you can see these images of the landscape on Titan as the probe was ascending. So at an altitude of about 100 miles, this is what it looks like. Very hazy, very cloudy, hard to see much. As you go lower, you can start to see surface features that look pretty similar to the surface features we see on Earth. You can see these mountains and these ravines. And as you go further and further down, you can see landscapes that look pretty similar to what we see here on Earth. And finally, this kind of rocky, hazy landscape from the ground. So Titan's a really intriguing place, and it will be exciting to learn more about what's going on this very unusual moon.